Hi everyone, welcome back. Nice to see lots of you joining. Going to give it a few more seconds. In the meantime, I've actually already had an answer question in the Q&A, which is this topic part of AQA for combined? Yeah, this is all of AQA. There's going to be quite a lot of higher tier stuff in here today. It's all really useful and interesting stuff, but yeah, that is just something to be wary of. Maybe you've not learned it in school yet, so don't be worried. It might be that you're not doing higher tier. So today's webinar is all about electromagnetism. It's quite a nice follow-on from yesterday because we're going to be talking about a lot of the same principles such as potential difference and current, but as the name suggests, we're going to be combining it with magnetism. As always, it's great if you guys could be really interactive because I can't hear you or see you. So by putting your answers in the chat box, I can gauge your understanding. And then put your questions in the Q&A. So it will really help me to see questions from answers and be able to answer questions a lot better than I did yesterday. I've got them on my phone as well, so I can see them coming through. So please ask lots of questions throughout the session, and yeah, let's get started. So this is a whole new topic, nothing to do with electricity. Electromagnetism is its own thing. Get time at the end, we might do a Kahoot. I've just seen that, and it's not just higher tier. So while I'm talking about electromagnetism, I'm going to put the answers from yesterday's questions on the screen. You don't need to be reading them. You don't need to do anything when you watch this back. When it's recorded, you can check your answers from yesterday's questions. Cool. So electromagnetism is all about how when we have current flowing through a wire, there is actually a magnetic field created around that wire. And that is what electromagnetism is based off of. Okay, you don't really need to know why a magnetic field is created, but you do need to know that it's created. And when it's created, these really weird phenomena start to happen. And this electromagnetism forms the basis of levitation. Okay, that's why I think it's actually a really cool topic. It's pretty hard to understand. There's a lot of higher tier content, but the things that it actually does is amazing. It can make things float. It can make things levitate. We can make things move without touching them. And that's why it's quite exciting. So this is what the AQA syllabus says that electromagnetism includes. It's got 3 topics, but there's a lot of stuff to cover. So permanent and induced magnetism, magnetic forces and fields form our first topic. Poles of a magnet and magnetic fields come under that. So that's all your really basic magnet stuff. North pole, south pole, magnetic field lines, compasses, that sort of thing. Not going to spend too much time on that because there's, again, as I said, a lot of electromagnetism to cover. The motor effect is that thing where I said we can make things move without touching them. That covers electromagnetism in general, what it is. Fleming's left-hand rule, which I'm going to attempt to teach you, although my camera is mirrored. So I'm going to change that so that it's not mirrored, so that you can actually see that I'm using my left hand and you can actually get the orientation right. Electric motors and loudspeakers. So how can we apply the motor effects, actually make it relevant in day-to-day life? Electromagnetism is not very useful in its own. And then third part is induced potential, transformers and the national grid. So we did touch on it yesterday, but I didn't really explain it too much. And this is, again, how we can create voltage basically out of thin air. Without a battery or a cell, we can actually make voltage just by using a magnet and a coil of wire. Yeah, so really cool stuff, really interesting stuff. And then we're going to look at the generator effect and how that applies to microphones and transformers. All really similar to the EdXL specification, OCR. They're all really, really similar, so don't worry at all. Okay, poles of a magnet. Don't want to spend too much time on this, but let's have a little bit of a refresher. On the top right, you can see this little graphic here, this diagram, where the top one is attracting, then we've got two norths, and then we've got two souths, which are repelling. So like charges, like poles attract, different poles attract and like poles repel. So a north and a south are going to come together, but a north and a north are going to repel, and a south and a south are going to repel. We've all done this at school, and we've all, I'm sure, tried to force them together or pull them apart and go against the natural magnetism. They are strongest, magnetic fields are strongest where our field lines are closer together. Okay, so if you look in the second graphic here, you can see that at the poles, the magnetic field lines are pretty close together. The closer the magnetic field lines, the stronger the field is at that point. So as they become further and further apart, that represents the magnetic field getting weaker and weaker. Now, a permanent magnet creates its own magnetic field. Okay, that is a permanent magnet. That's a magnet that will never lose its magnetism. It will be a magnet for life. Okay, and when we place that on a piece of paper, on a table, wherever it happens to be, a magnetic field is created around it, as you can see in picture A here. Okay, so this is our permanent magnet, our permanent bar magnet, sitting on a table, and around it, it creates a magnetic field. Okay, so a field is just this area that it affects and puts its magnetism into. Okay, and anything that is placed in that magnetic field will feel this magnetism. It will feel this magnetic force. Okay, it's the exact same with an electric field. Anything that you put into an electric field will become charged. Anything that you put into a magnetic field will become magnetized. And one really good example of that is an induced magnet. When we place magnetic material into a magnetic field, it becomes magnetized. Okay, so we're going to place our iron nail into our existing magnetic field, and what happens when we place it in there is that it becomes magnetized. Okay, this phenomenon is induced magnetism. It's induced because it's created. Induced is a key word that we need to talk about. Induced means created, and actually created in a sort of weird way, right? So induced means we do something else which creates this magnetism. And we're going to look at induced potential later on. What's special about induced magnetism is that it's always attractive. Okay, induced magnetism doesn't repel anything. Induced magnetism attracts magnetic materials. It doesn't have the ability to repel. When we take our induced magnet out of the magnetic field, it loses its magnetism. Okay, so it's a temporary magnet. It's only a magnet when it's in the magnetic field. When we take it out the magnetic field, it loses its magnetism. It's no longer magnetic. So two types, permanent and induced. Permanent, as it says, is a magnet for life, and it creates its own magnetic field. Induced magnet is a magnet that we put into an existing magnetic field. It gains magnetism, and when we take it out, it loses it. A good example of this is if we have a bar magnet, which is a permanent magnet, and we get a paper clip, which is magnetic material, and we put it into the magnetic field of the bar magnet, it gains magnetism. That paper clip becomes magnetic. When we take it out of the magnetic field, it loses its magnetism and it's not going to attract anything else. So this is the way that we make temporary magnets. Okay. magnetic field lines are these blue arrows here. I'm sure you've all seen them before, and they show the direction of the force if you were to put a north pole at that point. They always go from north to south. So you can see here on a bar magnet, they go from north into the south, north to the south, and north to south, but away from the north. Okay, you need to know how to draw these magnetic field lines, and you need to memorize them. A really good way to draw magnetic field lines is to take a compass and place it around the bar magnet and trace what way the arrow is pointing. That's going to tell you the direction of the force if you were to put a north pole at that point. Okay. We have compasses. We know that in a compass there's a little bar magnet and the north always points to the North Pole. What you might not know is that the Earth has a magnetic field. The Earth we can think of as having this huge bar magnet right down the center. Okay, so I want you to imagine a big bar magnet right down the center of the Earth. There is a magnetic South Pole and a magnetic North Pole, which is really confusing because the magnetic South Pole is the North Pole, and the magnetic South Pole and the magnetic North Pole is the South Pole. So we have North Pole and South Pole, right? Like Antarctica and Arctic, whatever it is. That's actually the opposite to how the bar magnet is placed. So the bar magnet, its North Pole, the bar magnet's North Pole is the real South Pole, and the bar magnet's North Pole is the real South Pole, and the bar magnet's South Pole is the real, I really hope you get the gist, but basically North Pole and South Pole are flipped for the bar magnet. Okay, enough of that. So let's go on to actual electromagnetism. As I said at the beginning, when a current flows in a wire, it creates a circular magnetic field around the wire. Okay, so you have all charged your phone, you've charged your laptop, you've all used a wire, right? You've all experienced a current flowing in a wire. Happens all the time around us. When a current flows through a wire, just as I've got my laptop plugged in here, when a current flows through the wire like it is now, a magnetic field is created around the wire. So it goes round like this, round like this, round like this, round like this. Okay. Outside of the wire, it's really, really weak. Inside of the wire, it's strong. The strength of the magnetic field is greater when we're really close to the wire, and it gets smaller and smaller and weaker as we get further away from the wire. Okay. So we know that we've got a wire, we've got a current flowing in our wire, and we know that a magnetic field is going to be created around that wire. But how do we know what direction the magnetic field is going to go in? Can anybody tell me how you know what direction the magnetic field goes? What rule can you use? Well, use the right hand grip rule, but how do you know? What do you have to do? What do you have to do? How do you perform the right hand grip rule? Look at arrows. Maxwell's right hand rule with thumb. Yes, good. See which way the fingers curl. Brilliant. Okay, so the way that we do the right hand grip rule is this. You're going to take your right hand. I want everybody to do this along with me. You're going to take your right hand and you're going to hold it like this. So just do a thumbs up. Okay. The thumb represents the current direction. If the wire is facing up, if the current is flowing upwards, the thumb points upwards and you see which way your fingers curl. Mine curl anti-clockwise. Okay, they curl towards me and background, which is anti-clockwise, like that. Then I'm going to take my thumb, I'm going to point it in the direction of the current downwards, so in the right-hand diagram. Yeah, so my thumb is pointing in the direction of the current, and now my fingers are curling clockwise. So my magnetic field is in a clockwise circular direction around the wire. So you're pretending that your thumb is the wire, this is all the wire, and you're going to point in which direction does the current flow. It's not going to work if you use your left hand and you're going to get the answers wrong. So you must make sure that you use your right hand for this. It gets even more confusing because later on we're going to look at Fleming's left-hand rule. But for knowing which way the magnetic field around a wire goes, you're going to use the right-hand grip rule. So current is represented by the thumb, and it's either pointing upwards or it's pointing downwards, and the direction that your fingers curl is what way the magnetic field acts. Okay, you can always do it left and you can always do it right as well. So if it's pointing to the left, then your fingers curl inwards towards the page. Okay. The strength of the magnetic field is, again, greater closer to the wire and increases if the current increases. Okay, a solenoid. Hopefully you've heard of a solenoid before. It's nothing really actually too complex within itself. A solenoid is just a coiled piece of wire. Okay, I can make a solenoid right now with my headphones. I can just wrap it around a finger and that's my solenoid. Okay, really, really simple concept. But solenoids are really powerful when we put a current through them. When current flows through a solenoid, the magnetic field becomes stronger. And the field inside a solenoid is really strong and really nice and uniform. Why do we think that the field inside the solenoid is much, much stronger than outside the solenoid? Put your answers in the chat. Why do you think that the magnetic field inside the solenoid, inside the coil of wire, is much stronger than it is outside of the solenoid? What's the reason? Okay, a few of us are saying because it's closer to the magnet. A few of us are saying that it's greater surface area. It's close to the magnet. Each coil has a magnetic field and they all add up. Yes, I've got it on the side, so you may have read it and spotted it already. But inside the coil, all the little individual magnetic fields of all of these wires add up inside. But outside, all of the little magnetic fields of each coil of wire cancel out. Okay, and that is why it's so much stronger inside than outside the solenoid. Now, we already know that it's nice and strong inside the solenoid. But when I put an iron nail, which iron is a magnetic material, inside that solenoid, I make it even stronger. Okay, so we wrap this solenoid around an iron nail and we give it a magnetic core. That iron core increases the solenoid's magnetic field strength. Okay, that is how we create an electromagnet. Okay, moving on. The motor effect. Has anybody ever heard of the motor effect before? What is the effect? What happens? Why does it occur? What can we do with it? What is the motor effect? What is the motor effect? Okay, guys, just if you can put your answers in the chat rather than the Q&A, that's really going to help me out. Okay, two magnets making a rod spin. The turning of a wire between a permanent magnet, good. When two electromagnets interact. Some really good ideas here, guys. So the motor effect is when we place a wire carrying a current in an existing magnetic field. Okay, we're going to place a wire that is carrying a current in an existing magnetic field. So an existing magnetic field comes from our bar magnet. It could come from just a permanent magnet. Okay, it has to be a permanent magnet. As we mentioned before, when we have a permanent magnet, that permanent magnet creates its magnetic field, creates its own magnetic field. Okay. If that magnetic field, we then place a current carrying wire into it, as you can see here by the red line, we're going to place our current carrying wire into this existing magnetic field, a force is created. Okay. Why is a force created? What is happening? What is interfering? What is creating this force? What's making it move? What do we think? Why does it move? It's a really weird thing to happen. Nobody's touching it. Nobody's moving it. So why is it moving? What is creating this force? What do we think? We know that it happens when we put a current carrying wire into an existing magnetic field, but why? Brilliant. Okay, somebody has written Arushi. Brilliant. So the magnetic field of the magnet interacts with the induced magnetic field of the current carrying wire. Brilliant answer. Well done, Arushi. And well done to those of you who also got the answer right. The wire carrying current, as we said, remember right at the beginning, any wire that carries a current has a circular magnetic field around it. Okay, doesn't matter what wire it is, doesn't matter if it's your phone charger, your laptop charger, or the wire in a circuit for your light bulb. Any wire that carries a current creates a magnetic field, which is no different to this red wire here. So this red wire has its own magnetic field, its own circular magnetic field around the wire. That circular magnetic field interacts and interferes with the existing magnetic field that we've placed it into. This interference of the two magnetic fields creates the motor effect, and it creates this force. Okay, so let's have a think. How do we know what direction it's going to move in? How do we know whether the wire is going to move down, whether it's going to move up, whether it's going to move left, or whether it's going to move right? How do we know? Well, this is where Fleming's left-hand rule comes in. And this is where you look really weird in the exam hall because you're doing this in the air and all the invigilators don't know why. And this is what you've got to do in the exam. Okay, so left-hand rule, first things first, it must be left hand. If you do it with your right hand, you're going to get all the answers the opposite way around and you won't get the marks. So it has to be your left hand. Okay, so we're going to use our thumb and our first two fingers, whatever you call them. I don't know if your first finger and your second finger, whatever, index and middle, has to be these three fingers. And we're going to hold them like this. Hold them like this, all at right angles to each other. So that's the right angle and then also a right angle there. Okay, so each finger has its own little thing attached to it, if you like. Thumb is motion. Thumb is motion. People like to think of it with the M. The M in thumb is the M in motion. Yeah, however you guys want to remember. So thumb is motion. First finger is field. So first, field. First finger represents the magnetic field, the direction of the magnetic field that we've placed our thing into. And the third finger is the direction of the current. So let's have a think. How do we do that for this example here? How do we apply Fleming's left-hand rule? So ignore the purple arrow for now, because that's telling you the motion. You never start with the thumb. That's usually what you're trying to work out. The exam question might be, using this diagram, tell me what way does the wire move? Okay, so we're going to place our first finger and our second finger in the correct direction. So first finger, field. The field goes from north to south, points from north to south, which in our case is from left to right. Okay, that's the first things first. Our field goes from left to right, north to south. Okay. Next part, third finger is the direction of the current. Now in our diagram, the direction of the current is facing away from us. But you'll notice that if you stick your third finger out, now it's pointing towards you. So you've got to rotate it. Okay, you've got to rotate it so that the current is now facing away. The middle finger, the current, is facing away, is pointing outwards or away from you. But the magnetic field is still pointing from left to right, still north to south. Then you stick your thumb out, and whatever direction the thumb is, that's the motion. Okay, your thumb is obviously not, is naturally gonna point in the direction of the motion. You don't need to really do anything with your thumb. It's gonna naturally point in that direction. So my thumb, and hopefully your thumb too, is pointing downwards, and that tells us direction of motion or the force. Okay, so our second finger, just to recap, is our first finger is our field. This one here, first finger is our field, which points from north to south or left to right. Second finger is our current, which goes away from us, and our thumb points in the direction of motion. Okay, hopefully you guys have got that. Feel free to practice on your own as well, and please never ever feel afraid to do that in an exam hall whilst you're doing your paper, because it's not cheating. You're not doing hand signals to anyone. The invigilators will understand. Okay, so please never feel embarrassed to do that. Don't try to do it in your head. There's a reason that Fleming invented this hand rule. Okay, so please use it. Okay, then we introduce our first equation. Luckily, there's really not that many equations in electromagnetism. This is the first one. So F equals Bill, or BIL. F stands for force, B stands for magnetic field strength, which is measured in Teslas, which is represented by a capital T. I stands for current, which we know is measured in amps, and L is the length of wire that is in the magnetic field. So from that equation, we can derive the fact that the force will increase if the magnetic field strength increases, the force will increase if we increase the current, and the force will increase if the length of wire in the magnetic field increases. Okay, so 3 factors which can help to increase force. So I is current, L is length, and B is magnetic field strength. Somebody said, do we always look at the diagram from our perspective? Great question, Remy. Yes, you absolutely do, always from your perspective. So as you're looking at it on your exam paper, you do it exactly like that. Okay, don't try to think about what the examiner's thinking or from the person who wrote its point of view. Just look at it and just do it from your perspective. Nobody else's perspective matters. Okay, great. So let's move on. Oh, someone just said, how did you know the current direction? You might not be able to see it, but there's a little arrow on the red wire there, the orange wire, pointing away from us. So that's how I knew. Hopefully it will be a bit more clear in your exam paper. That's how I knew. Okay. Now, not really helpful to make wires move on their own if we can't apply it. And this is where the electric motor comes in. So we have our magnetic field. We have a north pole on the left and we have a south pole on the right. That's our permanent magnetic field in which we place the wire. Just like before, we have a permanent magnetic field in which we place the wire. Exact same thing here. This time it happens to be a square wire. Okay, now the coil of wire, this single coil of wire, is allowed to move freely between two magnets, okay? It's attached to this split ring commutator. Commutator is just like a piece of metal, basically, which can reverse the direction of current. When a current is put through the wire, the coil moves. And we know that because of the interference of the two magnetic fields and the motor effect. When we place the current through the wire, it creates a magnetic field. That magnetic field interferes with the permanent magnetic field and motion is created. So this coil rotates and the direction of the current must be reversed every half turn, otherwise the coil comes to a halt again. Okay, so the coil is turned and then we must reverse the direction of the current so that it keeps turning. Okay, bit weird. We can't just expect it to continuously turn. We have to reverse, keep reversing the direction of the current. That's how an electric motor works. So this is a DC current coming in. The current goes into the left-hand side of the wire and creates a magnetic field which interferes with this north pole magnetic field lines and creates motion downwards, as you can see by the blue arrow. Then on the right-hand side, current flows through in the opposite direction, which creates an opposite magnetic field, which interferes with the existing magnetic field, again, to create motion, but this time it's going to move upwards. And because they have opposite motion, they start to move in a circle. Okay, so they move anti-clockwise. We can also apply this same phenomenon to a speaker. So a speaker contains both a permanent magnet, the yellow, and an electromagnet, the solenoid here, the coil of wire, the brown coil of wire. So the two poles of the permanent magnet stay the same as they always do, but the poles of the electromagnet reverse when the direction of the current reverses. This attracts and repels the electromagnet towards the permanent magnet. And this constant attraction and repulsion creates vibrations. Those vibrations vibrate the speaker cone, and so that moves too. And then the speaker cone is going to vibrate the sound particles in the air in front of the speaker, which is the sound that we hear. So it's this attraction, this constant attraction and repulsion of the permanent magnet and the electromagnet that creates vibrations that vibrate the cone, that then vibrate the air in front of the cone. Okay, induced potential. Induced potential is this really cool idea. You might want to think of it as induced potential difference because that's what it actually means. But it is this idea that we can create voltage by moving a magnet. Okay, we aren't using a battery. We aren't using a battery or a cell or an AC or a DC supply. We are just using a magnet and a coil of wire. Okay, there's no batteries, there's no cells, nobody's putting a power supply in here. We're inducing potential difference, we're inducing voltage by moving a magnet. Okay, so we can create potential difference when there is movement between a conductor and a magnetic field. This can happen by a coil of wire moving into a magnetic field or a magnet moving into a coil of wire. Either way, there needs to be relative movement between the coil of wire and the magnetic field. Movement is the key idea here. If it's not moving, there is nothing being induced. Potential difference will not be induced. Okay, if the magnet's there, stationary, out, nothing's happening. If the magnet's in and stationary, nothing is happening. It's only if it's constantly moving do we create induced potential. Okay, so as it's moving, potential is induced, but as soon as it stays still, that potential difference goes away. Okay, it goes straight back to zero. Only when we push the magnet in, when there's movement, is potential difference created. Okay. So if a potential difference is created, then a current is created too. As we know from yesterday, a potential difference pushes the electrons around a circuit and a current is created. Okay, so if we induce potential, we actually end up inducing current too. And this all happens by pushing a magnet into and out of a wire or a coil of wire moving in a magnetic field. Okay, so when we push the magnet into the coil of wire, there is an induced potential difference. Because there's induced potential difference, there's induced current. Okay, potential difference always creates a current. When we have a current, we create a magnetic field around the wire. Okay, so we've gone from inducing a potential difference to inducing a current to inducing a magnetic field. Remember, inducing just means creating. Okay, so we've got our magnetic field, and this new magnetic field opposes the original change. What I mean by that is if you push the magnet in, then the magnetic field is going to repel the magnet back out of the coil. Okay, so they oppose each other. So if a magnet is moved into the coil of wire, if it goes into the coil of wire, the induced magnetic field repels the magnet back out of the coil. Okay. Hopefully that makes sense. There's quite a few steps here. It starts with the induction of potential difference, then it goes to the induction of current, then because there's a current, remember, a magnetic field is created, and that magnetic field opposes the original change, in this case, the magnet going in. Okay, an induced potential difference or induced current will increase if the speed of the movement is increased, if the magnetic field strength is increased, or if the number of turns on the coil is increased. Okay, all three factors which we can use to increase voltage. An induced potential difference or induced current will change direction if the magnet is moved out of the coil or the other pole of the magnet is moved into the coil. Okay, so you need to know the three factors that will increase the potential difference and the three factors that will change the direction of the potential difference. Sorry, the two. Okay, so we then use this idea of inducing potential difference and of inducing current to invent the AC generator, okay, otherwise known as an alternator. So the coil is rotated in a magnetic field, And because it's moving and it's creating a magnetic field, current is induced in the rotating coil. So this again is an example of the generator effect. It induces potential difference. Okay, so because we have constant movement of a coil of wire in a magnetic field, movement between the conductor and the magnetic field, potential difference is induced. There is constant movement between the coil of wire and the magnetic field. If I just leave the coil of wire in the magnetic field, nothing is going to be induced. It's only because it's constantly rotating in the magnetic field that I get a potential difference created. This is all higher tier stuff from now on, by the way, guys. Okay, so this coil of wire rotating in the magnetic field is going to create, it's going to induce a potential difference, and therefore it's going to induce a current. But because it's continuously rotating, that means that the induced potential difference is going to constantly change direction. Okay, so it's going to go from positive to negative over time, otherwise known as AC, right? Alternating current, we looked at it yesterday. We also have the DC generator. It works on pretty much the same principle in the sense that there is a coil that is constantly moving in the presence of a magnetic field. However, it uses a split ring commutator rather than the two slip rings found in AC. So these are the two slip rings in an AC generator, but in a DC generator, we just have one commutator. Okay, so in a DC generator, otherwise known as a dynamo, the split ring commutator changes the coil connections every half term. And because it keeps it in the same direction, a DC current is created. Okay, it's always in the same direction. This is just allowed to continuously rotate. But in a DC, we constantly flip the current so that we have the potential difference always in the same direction. And over time, it's always in the same direction. It's always positive. Okay, microphones. Microphones use the generator effect to convert sound waves into electrical signals, and they work like this. So pressure variations in sound waves coming through from your voice cause the diaphragm to vibrate. The vibrations of the diaphragm cause vibrations in our coil, which cause it to move, right? It's vibrating, it's moving. And remember, a moving coil in a magnetic field will induce a potential difference. Okay, so it's those vibrations from your voice that then vibrate the moving coil. And because the coil is moving in a magnetic field, a potential difference is induced. The induced potential difference causes a current. As we know, potential difference causes a current. And the changing size and direction of the induced current matches the vibrations from your voice. And then those electrical signals are generated into sound waves, which are louder than the sound waves that you spoke into the microphone. Hopefully that makes sense. It's the vibrations of your voice which move the coil. And because the coil is moving in a magnetic field, potential difference is created, it's induced. Because potential difference is induced, current is also induced. And because current is induced, we have a complete circuit. The changing size and direction of the induced current matches those initial vibrations of the coil. Okay, so pitch and loudness are going to affect the size and direction of the current. So fluctuations, constant changing of the current, then creates pressure variations in the sound waves which are going to release from the microphone. Okay, I want to point you guys out to these four applications of electromagnets: the scrapyard crane, the circuit breaker, the electric bell, and the relay. We won't have time to go through them today, but I'm going to go through them on the slide so you guys can read the applications of them. These are ones that sometimes come up in exams, so it's useful to know. Okay, I'm going to go on to transformers now. So transformers are these devices that can increase or decrease the voltage of an alternating current. Okay, they can increase or decrease the voltage of an alternating current. So it's a way of increasing voltage or current, but without having to add cells or take cells away, or replace the battery with a smaller one or a bigger one. Okay. It's a really, really great way. It doesn't really require much energy. It's actually just a magnet. So this is a transformer, this big metal rectangle, and it's made from a big rectangular magnet with two coils wrapped around each side. The left-hand coil is the primary coil and the right-hand coil is a secondary coil. Okay, AC, alternating current, comes into the primary coil, and AC leaves through the secondary coil. There are two types of transformers. First one is a step-up transformer. A step-up transformer increases potential difference. A step-down transformer decreases potential difference. Okay, the way that you can tell is the number of turns. So if the number of turns is bigger on the primary coil and smaller on the secondary coil, just as it is in the diagram, then that's a step-down transformer because it has less coils. Okay, so this rectangular magnet is an iron core. We use iron because it's really easily magnetized and it carries the magnetic fields that come from this coil of wire. So how does it work? So a primary alternating voltage drives an alternating current through the primary coil. So we have an alternating current through this primary coil here. That primary coil creates a magnetic field. We know that any current carrying wire creates that magnetic field. Okay. That magnetic field will change as the current changes. The iron core then increases the strength of the magnetic field, and the changing magnetic field from the current induces a changing voltage in the secondary coil. The induced voltage produces an alternating current in the external circuit. Okay, guys, this is higher tier stuff. It is super complicated. So I've tried to break it down into these 7 steps for you. So the primary voltage comes from the power station, okay, wherever it's coming from. That, because we've got a voltage, we have a current, okay, they go hand in hand. Primary voltage creates a primary alternating current. Because there's a constantly changing current, there's a constantly changing magnetic field. That's strengthened by the iron core, and that changing magnetic field goes on to induce a potential difference. That induced potential difference then creates an induced current. And that's how a transformer works. Then we come on to our second equation, which is the transformer's equation. So we have primary voltage over secondary voltage is equal to the number of turns in the primary coil divided by the number of turns on the secondary coil. It's not really like any other equation we've seen before. But if your fractions match, then you know that you've got it right. Okay, so you might be given, I don't know, let's say that the primary voltage is 3. Primary voltage is 3. And the secondary voltage is 6. So primary voltage is 3. And the secondary voltage is 6. Okay, my computer's being really slow, so we're going to leave that. And as long as you get an equivalent fraction on the other side, then you are good. Okay, so it's not really one of those ones that you can put into a triangle. It's about the ratios. It's about the fractions. Does your ratio on the left match your ratio on the right? And if it does, then you've got your transformer equation correct. Okay, step up or step down. How do we know? Step up, well, our number of coils on the secondary is going to be bigger than the number of coils on the primary. A step down is the number of coils on the secondary is smaller than the number of coils on the primary. Now, you need to remember that transformers only work when we have alternating current. They don't work when we have direct current. Direct current doesn't work because there's no changing current and therefore there's no changing magnetic field. A changing magnetic field is necessary to produce alternating current. Efficiency. Transformers are really, really great. They're nearly 100% efficient, which means that the power that we put into it is nearly the same as the power that comes out of it. As you might remember, power is equal to voltage times current, and the primary voltage and the primary current, when you times them together, gives you the primary power. The secondary voltage and the secondary current, when you times them together, gives you the secondary power. So again, if your left-hand side matches your right-hand side, then you have perfectly efficient transformer. Okay, so this is a perfect case. It doesn't work really in real life, but we say that for the purposes of the exam, transformers are 100% efficient. Okay, for the purposes of this equation, the power that goes in equals the power that comes out, which you can test by doing the voltage times the current in equals the voltage times the current out. Okay, that brings us to the end. We'll go through a few questions and I'll try to answer your guys' questions as well. Someone said, please, could you go over the difference between split ring and slip ring commutators? Okay, so here in an AC generator, we have 2 slip rings. Okay, these 2 slip rings are connected to the coil, and that is what allows the coil to turn. In a DC generator, we have a commutator. Okay, we have a split ring commutator. And that means that the coil is allowed to rotate half and then it gets switched and then it gets switched and then it gets switched. Okay. Okay, so for the last couple of minutes, let's have a go at attempting some transformers questions, because I think that these ones can be quite tricky because you've never really seen an equation in this kind of format before. So there are 500 turns on one coil of the transformer and 20,000 turns on the other coil. Use the equation to work out or to calculate the potential difference across the secondary coil. Okay, so what we need to do is, first of all, we need to work out the right hand side of the equation. To do this, we need to do 500 divided by 20,000 and put that into a calculator. And that needs to be equal to the PD across the primary divided by the PD across the secondary. What is 500 divided by 20,000? .025, and that needs to be equal to the left-hand side of the equation. So we've worked out the right-hand side of the equation. Now we work out the left-hand side of the equation. So the PD across the primary coil divided by the PD across the secondary coil is 0.025. Given that the PD across the primary is 10 volts, what is the PD across the secondary coil? Can anybody work that out? If you can, put your answers in the chat. What is the PD across the secondary coil? Given that the PD across the primary is 10. What do we think? Cool, lots of you writing 400. That is absolutely the correct answer. So what type of transformer would this be then if the PD across the secondary coil is bigger than the PD across the primary coil? What type of transformer is this? If we have a bigger voltage being created than we did at the beginning, what are we doing? Good, it's a step up transformer. It's stepping up the voltage. It's increasing the voltage from the primary to the secondary. Okay, I'm going to flash some questions for you to have a go at on the screen. Pause the video when you're watching it back. And again, I'll put the answers to these questions in tomorrow's session at the beginning so you can check. I hope you guys have learned lots today. Remember this has been recorded, so you can go back and watch it in your own time, revise, try the questions and check your answers with tomorrow's webinar. Cool, that's all from me, guys. I hope you have a lovely evening and I will see you in tomorrow's session for nuclear physics, where we're going to be looking at fusion and fission processes and how that relates to the life cycle of a star.